Good to see you.
Good morning, Mr. President.
Good morning. What's your name?
So I'm Ty Garrett-Mills.
Good to see you. Ty is spelled how?
T-I-Y-E.
T-I-Y-E. Good to see you. And we got a leaf
Yes, we do.
and a fossil.
Yes. Would you like to hear about my project?
I am thrilled to hear about your project. First of all, where are you from?
I'm from Denver, Colorado.
Okay. And what grade are you in?
I am a junior in high school.
You're a junior.
Yep.
So you're going through the whole SAT application process, all that stuff.
Yep.
Yeah. It's a busy year.
Yes.
But not too busy that you couldn't pull off some outstanding projects. So let's hear about what exactly you're doing.
Alrighty, so I'm assuming you've seen a leaf before.
I have.
Alrighty, so if you look carefully,
Yeah.
every leaf has a system of veins.
Right.
And these are called leafination systems.
Right.
And these are very important to scientists because they can tell us all sorts of things about leaves.
Right.
So right now, because there are more than 350,000 species of flora and fauna on the planet,
Right.
we are trying to keep track of them all. So the eventual goal is to basically have a registry online of leafination systems so that scientists can share knowledge over the internet instead of having to send samples back and forth.
Right.
That's costly.
Makes sense. Right.
So the current way to do this has many problems. It's very, very expensive, and it completely destroys the sample. So I tried to see if there was a more economically viable and efficient way to do this. So I looked at the most advanced research, and this man discovered that X-ray photons were really helpful in imaging leafination systems.
Okay.
So at first, my first thought was, I'm going to build an X-ray machine.
Right.
So I got online and I found the original blueprints for an X-ray machine and
Right.
quickly discovered that was not the direction to go in because it's dangerous, it's not economically efficient in any way. So
Right.
I thought to myself, why does it have to be X-ray photons?
Okay.
Why can't it be another light source?
Uh-huh.
So I ended up using the LED flashlight on my iPhone and a scanner that was purchased by the Denver Museum of Science and Nature, which is where I hail from. I was a part of the Teen Science Scholars Program.
Right.
And I discovered that if I scanned the leaf,
Yeah.
normal scanning,
Right.
and I shined my iPhone flashlight over it, I was able to image leafination systems successfully. So
There it is.
sort of as a basis of comparison, this is the one that was done professionally.
Yeah.
Thousands of dollars,
Right.
lots of hours, and then I was able to do this one in about 2 minutes on my own.
Even better.
Yeah, and one of the reasons why this project is important is because recently in science there has been a big leap to get citizens in science because there simply aren't enough scientists to do it all.
Right.
So by having citizens collect data, scientists can analyze it and draw their own conclusions.
Right.
So the thing about this process is everyone has an iPhone nowadays, so it's easy to have access to that, and a scanner is basic office supplies. So if I was just able to teach people this technique, we could have citizens uploading images of leafination systems into their computers, and we could pick the best ones and use them online for the registry. And the reason why I was able to do this project is because I had an internship in paleontology in the summer of 2014, because leafination systems can help us track evolution in plants, which is one of the reasons why I have the fossils here.
Yeah.
And so that's one of the reasons why I was able to do this, is because I had support from the Denver Museum of Nature and Science, and I had mentors and adults backing me, but this was me.
Were you always interested in geology?
I've actually always been interested in leaves and plants. So when I was younger, I did my very first science project when I was a first grader. I looked at algae, and I tried to see which lake in Denver had the most algae.
Uh-huh.
And then as I went to middle school, so the Denver Museum of Nature and Science hosts an annual science fair called the Denver Metro Regional Science and Engineering Fair.
Right.
And the first year I got an excitement award. The second year I won the science fair and got to go to state. And I won a national science fair as well. I took second place at the National Society of Black Engineers Science Fair. And then in my 8th grade year, I took third place. And each time I did something concerning leaves, but this was really my first time doing anything with leafination systems.
Now, one last question on this. Was there a particular technique that made the scanner with the LED light work best? And did you have to try a bunch of different techniques out? And did you just kind of arrive at this on your own? Or was there sort of a theory that allowed you to say to yourself, this might work?
So it was towards the end of the summer when we were supposed to be wrapping up our research project when I discovered this. And I discovered it completely by chance.
Yeah.
As I had been
Which
messing
is true
around.
for a lot of scientific discoveries.
Yeah, so I have just been messing with the scanner, and I was like, I don't know what to do at this point. Maybe I should have built the X-ray machine, which I'm really glad I did not go that route. And so I was like, well, I was pretty desperate. So I just shined it, and it worked. And one thing that I found is the further away you hold the light, the better the picture of illumination. And one thing that I did was I tried sprinkling water on the leaves, because there's a substance called perfluorohydrophenethrin, which is the only 30-letter word I know, and
And you pronounce it really well.
Thank you, and I enjoy saying it. And the thing
I'll
is,
test you guys on that pronunciation.
so it worked really well with X-ray photons. So I was wondering if it would work with my method. However, I got online and quickly arrived at the conclusion that it was too expensive. So I would like to try it with that. But another thing that I found that helps imaging leafination systems is there's this packaging plastic called polyvinyl chloride. And if you put a sheet on top of it before using the flashlight and imaging the leaf, it creates a better image.
So what do you want to do with all this knowledge?
Well, one of the things is I'd like to teach it to other people so that we can get the citizen scientist movement taken off the ground.
Yeah.
And eventually, because this is my junior year of high school, so people are asking me a lot, what do I want to be when I grow up? And I think I want to be a biotechnical engineer.
Excellent. We're so proud of you. What a great presentation. Come on, let's get a good picture. All right, look at Pete right here. Were your parents in class?
My mother is a doctor, and my dad is a director of his own school.
Okay. So you have to do pretty good at school. Otherwise, you're going to be in trouble at home.
Yeah.
Well, way to go. We're so proud of you. It's a wonderful presentation. And you really explain it well. Even for lay people like me. Good luck to you. That's wonderful. Hey, how you doing?
Good morning, Mr. President.
What's your name?
My name is Harry Paul. I'm from Long Island, New York.
Good to see you, Harry. What do we got here?
So I was born with congenital scoliosis,
Yeah.
and when scoliosis happens so early in development, there's really not enough space for the heart and lungs to develop.
Right.
And the treatments that they do currently are highly invasive.
Right.
Because you put the rods in, and you have to keep lengthening them.
You have to repeat it over and over
Yeah,
again. I was reading about this. Yeah.
That's what happened to me.
Yeah.
And it works, but it causes.
It's painful. There's all kinds of complications potentially.
I'm out of
all that
school
stuff.
and
Right.
things we don't want to happen.
Yeah.
So what I did is I designed an implant. This is an exaggerated version of it that grows along with the child's spine and keeps it straight as growth is happening, so that you can have more space between surgeries and reduce the number of surgeries overall.
What's the principle that allows it to adjust as you grow?
So it's all in the shape and the size of the tracks. So I had probably over 30 or 40 versions of this that I kept doing something called finite element analysis on, that sort of looks at the mathematical stresses of it to minimize them so that they won't break. And I sort of added in all the different features based on what I was reading and how I was seeing it work. But the problem is that something being strong enough doesn't mean it's going to work.
Right.
So really the only way to test that out is to either put it in an animal or human. And I didn't want to do that, and I couldn't do that.
Right.
So instead I made my own by building a mechanically growing model of the spinal column. You see here that, so I 3D printed each vertebra, and I put gears and screws inside of each one that simulates the natural growth the child would go through, so that when I attach the drill, they separate. And this is sort of the actual version that I was able to make of this implant. And this should have, based on these springs, a 50-degree curvature right now. But my implant and the rods are keeping it straight and allowing the growth to happen.
So at what age did you decide, you know what, there's got to be a better way to do this, and let me start kind of reading up and thinking about it?
So my first surgery was when I was 2.
Right.
And it was a few years later, really when I started in high school, and I knew I loved science, and I knew I was interested in research. And so I remember one night I just went on my research database and I Googled scoliosis. And the first article was by my surgeon, Dr. Gawati, who had talked to me about what was happening to me all throughout. And I was like, hey, maybe I'm onto something. And so I just read everything I could. And as I was reading what was out there and what people had been working on, I sort of came up with my own ideas of what I thought it should be. My first model was horrible. I don't want to look at it again. But I worked on it for 3 years and developed this, and now I'm working with an engineering firm in Virginia to hopefully bring it to market.
How how are you going to be able to test it? You've obviously modeled it and simulated it, and I'm assuming that some computer models could also help.
So,
But at some point, this is about as complicated a medical device as you can imagine, right? So for it to actually be implanted in somebody would require all kinds of complicated FDA approvals.
Yeah.
How do you go about that?
so the way I looked at it was in balancing the strength of the implant with the functionality. What's strongest is just going to be a sheet of metal.
Right.
That's not going to break. But in children, you can't do that. So when an adult has scoliosis, that's what we do. We put screws at every level and rods and plates along it, and that keeps them really straight.
Right.
But when you do that to a child, they won't grow anymore.
Right.
So it's a matter of allowing for the most growth that's going to be able, while still preventing the curvature from getting worse.
Right. How are we going to be able to test it out, though?
So we test it in other bone models. So you can implant something like this in a bone that doesn't have scoliosis pretty easily. So instead of curving the rods, you just put the rods in straight and make sure that it works. So you could do that on someone's leg, in an animal spine, anything like that.
I see.
And you use the mathematics of finite element analysis to sort of equate the two of them and make sure that the computer model and the physical model is working the way that it should.
Are you in college now?
Yeah, I'm a freshman at Tufts University.
Fantastic.
And I love it.
This is so impressive.
Thank you so much.
I'm so proud of
It's great to meet
you.
you.
I can't wait to see it work, and the notion that you take your own experiences and be able to apply it. What a powerful story that is.
Thank you. Thank
and
you.
inspiring for other people who are suffering from the disease.
I think it's always good to take a bad experience, and if you use it to do something, makes it a whole lot better.
Really proud of you. Come on, let's
you.
get a good picture. Where's Pete? There he is. You never know where Mike. Fantastic.
Thank you.
That's great.
Nice to meet you.
Thank you. Hi, how are you?
Good, how are you?
What's your name?
I'm Anvita Gupta.
Yeah. Good to see you. And what do we got here? What are we working on? First of all, where are you from?
I'm from Scottsdale, Arizona.
And are you just starting college or still in high school?
I'm a high school senior.
High school senior. Where are you going to go next year?
Still waiting for all the decisions to come back.
Fantastic. So what do we got here? What are we working on?
We're working on drug development. So it currently takes about 10 years and $5 billion to bring a single drug to market, which is a real problem when we're looking for drugs for diseases like Ebola or finding new drugs for cancer. So what I did was I developed a novel approach combining artificial intelligence and biochemistry to train the computer to autonomously find drugs for diseases like cancer, tuberculosis, and Ebola.
Right.
So my algorithm was able, when applied to the cancer protein thrombin, it was able to find an FDA-approved thrombin inhibitor and rank it first out of 3,000 other FDA-approved drugs. And I was actually able to find 4 new inhibitors for tuberculosis. They're natural compounds, and using my algorithm, and they've been experimentally validated in the lab.
What's the concept behind the algorithm?
Okay, so the algorithm is so unique and generally applicable because we target intrinsically disordered proteins. So these are proteins that change shape constantly. They're discovered recently. And when mutated, they cause a lot of different diseases. But finding a drug for them is really difficult because it's like finding a key for a lock that keeps changing, right? So my approach was a little bit different. I looked for a drug that mimics the part of the disordered protein that does the binding. And so what we can do is we can basically trick the other proteins in your cell into binding to the drug instead of binding to the disordered protein. And in that way, we're kind of able to block the disordered protein from doing anything and treat the disease.
So are you you're applying the algorithm to existing drugs that are already out there?
Yeah.
To see if they have new applicabilities?
Yeah, that's what we did for tuberculosis and also for Ebola. Because that's really good for finding drugs way more quickly, right? Because you've already tested those drugs and they've been shown to be safe in humans.
Right. So you're saying, and you're finding that the algorithm, it's already been validated
Yeah, exactly.
in subsequent studies.
Yeah, it's been validated for cancer, tuberculosis, and we're still looking for ways to test the new Ebola.
Sounds like a pretty powerful algorithm.
Yeah.
How'd you come up with it?
So the way they find drugs currently is they order thousands and thousands of them and they start pipetting against the protein. And I started reading about these disordered proteins and I thought that there had to be a better way to do it. So I just tried to look for the most elegant approach I could find. And this was it.
Just saying. I don't know what y'all have been doing. But this is what she's been doing. So I assume that you want to continue in this field.
Yeah.
And in light of all the breakthroughs that are being made in terms of genetic sequencing and being able to combine big data pools with algorithms like yours, potentially, we can short circuit pathways to discover potential cures for every disease.
Yeah.
We'll still have to do clinical trials, but but what this does is it narrows very rapidly sort of what might work and what might not work, and
Right.
could really compress then the length of time between
Exactly. Yeah,
us thinking we've got a lead and then actually bringing a drug to market.
because we use simulations right now to test almost everything from like diapers to
Right.
cars, and I think medicine should be reaching the same
Yeah.
point. So that's really what I've been working on.
Well, Holden, where's Holden?
Over here, sir.
So we're going to put this young lady in touch with our precision medicine team, right?
You bet. Absolutely.
Because we just launched a big initiative around these kinds of things. So you should, don't you think she should be
I'll give her my
interning?
card right now.
She should be working on the team.
That sounds
All right?
great.
Because we got a big push, and NIH is doing a lot of this stuff. Excellent. Come on over. There you go. Fantastic. So proud of you.
Thank you very much.
Thank you. How are you?
Good morning, Mr. President.
What's your name?
My name's Sahil Doshi, and I'm
Sahil?
a freshman in Upper
Freshman?
St. Clair High School.
You're a freshman at St. Clair High School.
Yep.
So what do we got here?
We got a revolutionizing energy storage device that uses carbon dioxide to generate electricity.
Okay.
Okay.
Show me what you got.
All right. So first, I came up with the idea by thinking of two of the biggest global problems in the world: the energy crisis in developing countries and carbon dioxide concentration in the atmosphere. So me being a natural problem solver, I thought, how can I connect these two problems together? And that's when I came about thinking about a battery that uses carbon dioxide. And so my first tests involved actually testing how does carbon dioxide affect the cell potential. And I found that as you increase the concentration of carbon dioxide in the electrolyte of a battery, it significantly improves the cell potential, as shown with the orange line and the yellow line. They are significantly outperform the other batteries. And
How so?
so-
Why is that?
the reason that happens is because carbon dioxide with water is called carbonic acid, but it has a weak pH of only 6.5 as an acid. But the more carbon dioxide you put into a solution or you put into water, more carbonate ions and bicarbonate ions form, so it's more ionically conductive. And so the more ions there are that are available in the cell, that means the cell potential will increase. And so if you can increase the carbon dioxide and put it in a small concentration, you're going to significantly improve the voltage.
Right.
So once I had that solved, I had the carbon dioxide in my battery, so I'm thinking, okay, what else can I implement? What else can I do to make this environmentally and economically friendly? I thought about recycled materials, because if we can use recycled materials that are brought from the consumer, we would fulfill one of the biggest economic theories in history, which is money flows between producers and consumers. Why not materials? So let's say I'm a consumer who has a recycled aluminum cans, but I'm just anyways going to throw them away. Why don't I turn them into like a corporate office, and the producer would pay the consumer for turning in those materials, would compile the battery together and sell the battery back to the consumer. So it's a
Okay.
direct to consumer connection,
Right.
and the consumer saves money. And so with all that in mind, I thought, okay, this is going to be my final product design. I had aluminum foil, a commonly recycled material, and silver-plated copper guitar strings, which is a really big issue with guitar players. We change our strings every month or so. So
You play
we
your guitar, you're a guitar player?
Yeah, I'm a guitar player.
Okay, all right. So you had a bunch of old copper guitar strings.
Yeah, I had a
lying
lot
around.
left.
Had to do something.
Yep.
All right.
So, and then my salt bridge was a 3M scouring pad. Again, going back to that recyclable material
Alright.
aspect. And then I had my electrolyte was sodium chloride, liquid ammonia, and carbonic acid.
Okay.
And the latex material was used to separate the cells from one another. And so this product, right now I have a patent pending on it, but I see a bigger vision for energy in and of itself. I see a CO2 capture system and a energy generation system all happening in one confined space. And that's what I'm working on right now over here. So these are just a couple of failed attempts at developing that CO2 capture system. So I started to think about, how do humans breathe? We breathe in oxygen, but we breathe out carbon dioxide. So if I reverse the process, theoretically, I should be able to take in carbon dioxide and release all the other gases that I don't need. And so here's an example of me trying to replicate the pressure gradients that happen within our lungs and in the atmosphere. And the balloon was trying to represent how our lungs expand. The balloon would expand, sucking in the air, and then when it would contract, it would let go of the air. And so this was the CO2 capture aspect of my cell. And eventually, 3 to 4 years down the road, moving forward, what I intend to do is I intend to have the CO2 capture aspect on the top of this box. And on the bottom would be the energy generation system. So the entire thing's happening in one box, user-friendly and easy to use. And then all the energy is being wirelessly transmitted to nearby sources so that there's no need for cables or anything of that sort.
Well, I tell you what, you're going to be busy over these next 4 years.
Yeah, I'm
Yeah,
definitely busy.
you're just a freshman in high school?
I'm a freshman.
Man, way to go.
Thank you very much.
All right, come on. Pete. Fantastic.
Good luck on your racket.
It's already going on.
Thank you.
It's over. It's over. How's it going, team? Good. We got an outstanding rocket team right here. What's your name?
My name is Amari D'Souza.
Hey, Amari. How you doing? What's your name?
My name is Gabriel St. Kitts.
Good to see you, Gabriel.
Stephanie Bullock. Good morning, Mr.
Good to see you, Stephanie.
Shamika Stanley.
Shamika, good to see you.
Maria Hewitt.
Maria, good to see you. And where are you guys from?
I'm from the U.S. Virgin Islands.
The U.S. Virgin Islands, and you guys are the rocket team for what school?
Elena Christian Junior High School.
Outstanding. So, tell me about how things have been going.
Things are going great. We're launching the Team America Rocketry Challenge, which is the world's biggest rocket contest.
Right.
It hosts 700 teams and about 5,000 students.
And out of those 700 teams, only 100 teams qualify to the finals.
Right. So, how did you guys get involved with the rocket team?
Well, there is a local club on our island at the school, and it's funded by our advisor, Mr. Steve Bullock. And these are students who have a passion in rocketry, so they join the competition, and for 6 years so far, we have competed in TARC, Team America Rocketry Challenge.
So, how are you feeling about your model for this year? Good?
Confident, very confident.
You feel confident?
Oh, yes.
I like that. You sound confident.
Thank you.
What refinements have you made to your model that makes you confident that this thing is going to go gangbusters here?
Well, as you can see right here, this rocket right here is our rocket that we are currently going to use for Team America Rocketry Challenge.
Hold on a second. I want everybody to see the rocket.
Okay, so you see, as you can see, this rocket right here, there are two different nose cones. This one is a pointed one, and this one is a rounded, standard nose cone. The reason why we use this one is because it's lighter in mass, and we're trying to be in a range of a certain weight for our rocket. So for our competition, we calculated that the specific weight for us to get for our criteria is at least 17 ounces. So TARC, Team America Rocketry Challenge, has 3 criteria. It has a height objective, a flight duration objective, and a payload objective. For the height, it has to go at least 800 feet, flight duration 46 to 48 seconds, and a payload of 1 raw egg.
There's the egg right there.
Right there.
That's the payload.
Yes, it is.
Okay.
Our astronaut. So in different years, the criteria is changing because TARC wants to spawn new creativity for all the teams. So, for example, in different competitions, the height could be in the 700 range, 700, 725. The time range is a different range, and the payload can also be 2 raw eggs instead of 1. And they might have to face vertical or horizontal in our payload section. Right. So right here is our payload section. We wrap our eggs in bubble wrap because this is the most successful thing we have used so far. Right. So our 1 raw egg vertically goes right in here. Right. And right below our payload compartment is our altimeter bay. This is a unique component of our rocket because we came up with the idea. If you look at a computer,
little circuit going on.
Yeah, if you look at a computer motorboard, you know there are different parts connected to the general motorboard. So we came up with the idea in using a hard cardboard material and attaching our altimeter to it. Therefore, it would prevent any type of malfunction or it being damaged while it's in the rocket. So we put 2 slots on either side of our altimeter bay and just slide it in, and therefore there's no way of it moving around when our rocket launches. This is our last component of our rocket. This is our engine mount component. This is where we hold our engine, and the engine that we use is the F20-4 engine. This engine, we have tested it many times, and it gave us our required height of at least 800 feet. And of course, these are our fins. We have a specific design for our fins because we use balsa wood for one, And our fins is very thin, so it's more aerodynamic and it will cut through the air and it would make it fly faster and reach to our required height.
So you feel pretty good about it, huh?
Of course, I feel very confident about
So,
this
so,
record.
so when's the actual contest?
Well, the actual contest takes place in May.
In May, huh?
At Manassas, Virginia.
How exciting!
It is very exciting.
Well, I want to wish you guys all the luck. What grades are you in?
I'm in 7th grade.
7,
I'm in 12th.
12,
I'm in 8th.
8.
I'm in 10. Someone.
Okay, so we're well represented.
Yes, we are.
7th to 12th. Come on, let's get a good picture. But Pete, we got to make sure we get the rocket in here. So let's slide over just a little bit. So Pete, maybe you can. Here, why don't you get in front of me, young lady? Right here. There we go. That way we can get everybody in.
Okay, great.
Good luck.
Thank you.
Proud of you. Huh? I hope all of you continue to study science and math.
Oh yes, of course.
Huh?
STEM.
And for some symbol.
How are you? What's your name?
My name is Sergio Corral.
Sergio?
So
Good to see you. Where are you guys from?
from Carlton High School in Phoenix, Arizona.
Phoenix? And this is your robot?
Yes. So I'm guessing you're familiar with FIRST, right?
I am familiar with FIRST.
So this is last year's robot. So we had 6 weeks to build this specific robot last year.
Right?
So what we have pretty much had to do that last year was we had to get a ball and we picked it up from the bottom here, and then from then on it went onto our catapult, and then it threw on into certain goals, different points for higher and lower
Right.
ones.
Another objective of the game was that you had to pass from one robot to another.
Right.
And so if you just got the ball and just shot it yourself, you would get 10 points. If you got the ball, passed it to one member, then that member passed it to another member, and then you guys shot it, you would get 40 points. So they kind of emphasized the cooperation with your team in that game. And some design features of the robot in order to complete the task. We have these aluminum arms that are controlled with a mini sim motor that have preset places that we want. We have a potentiometer here that senses where the motor is, and so we have 2 positions. We have the down position, which we use to grab the ball when it's on the ground, and then we have the up position that we use to grab the ball, that we use to place the ball on the catapult and also grab any balls that get thrown at us. And so with this potentiometer, we can go to both positions really fast using code. In order to throw the ball, we have these two giant pistons that are controlled using pressurized air. So once we get the ball and we put it up here,
All right. Watch out, Pete.
it's not. We then shoot it using pressurized air out like that.
How far to go?
The goal is about 6.5 feet tall, and it's pretty wide. So depending on where we are on the field, we shoot it differently. So when we're about in the center of the field, we shoot it really hard, horizontally, because we're pretty far away, so it has enough time to travel. But when we're like really up close to the wall,
You want a little more loft.
yes. And so it's really hard to do that with just pneumatics because it's kind of hard to control it. So like with the motor, you can tell it goes this speed and it'll go slower. With pneumatics, you kind of just have on or off.
Yeah.
So what we did was we added these 2 little foosballs here that are connected with 2 little pistons. And so when we shoot these out, they kind of have air in it, so they'll go down. But when we shoot them up, the ball changes position from where it starts. So when the foosballs come up, the ball goes like this. And so it gives it less time to stay on the catapult,
Right.
so it leaves the catapult sooner, and all the force would be going in the vertical position, so it'll go higher, loft pass kind of thing.
That's great. How long did it take you guys to get your design right and then actual construction?
So we usually try, first day we're on trying to make sure that we know, okay, what do we want to do, what's the points
What's
we
the
want to go
concept,
for,
yeah.
And then it usually takes about a week, and that's about the only time we want to spend on it, because right after that, since we only have 6 weeks,
Right.
we have to build the rest of the robot.
Right.
So as fast as we can get the design done that's when we start building it.
Another pretty cool, sorry to interrupt.
No, please
Another pretty cool feature we had on our robot, we currently don't have it on because we borrowed it from a mentor, but we had what was called a LiDAR sensor here in the front. Are you familiar with the
No.
LiDAR sensor? So what it does is it shoots waves out, and then it waits for the waves to come back, and so it tells it if there's something in front of it. So if we shot it right now, it would hit about where that table is and then
Right.
come back, and it'll tell you there's something that far away. So we use that to kind of take the human out of the equation when we're running the robot. So when we're going to get a ball, if it's just standing there, we drive to it. The LiDAR sensor thinks the ball is getting rolled over here, and so it senses the velocity and how far away it is. So once it's close enough to our grabber and since it knows its velocity, it knows exactly when to close the arms.
And it was doing that automatically.
Yes. And since we have it on this rotating arm, when we pull this arm forward or up, we can also catch balls that either humans or other robots throw to us. So when they throw the ball, the sensor is facing this way, and the arms are open. Like that. And so it works the same way as if it was on the ground. It senses the ball coming, and once it sees it's close enough, the arms close.
Now, do you have a name for your robot?
Lorenzo's dream.
Lorenzo's Dream. Pretty good. Come on, let's get a good picture. Make sure Lorenzo's Dream is in the picture. I'm so proud of you guys.
Thank you.
Keep it up. All right? Hey guys. Hello. What's your name? Can I shake your hand? Good to see you. What's your name? Good to see you, Caritha Jane. What's your name?
Emery Dodson.
Hi, Emery Dodson.
Addie O'Neill.
Good to see Addie O'Neill. And what's your name?
Alicia Better.
Well, tell me about your experiment. Tell me about your project. Who's gonna go first?
Emily.
Okay, Emily, what do you got?
We are the Supergirls for Girl Scout Troop 411.
Which is why you guys are wearing capes. Okay.
We looked at different tools that are used in education and learning, including Unifix cubes, computers, and smartboards. We decided that books are a great learning tool. Some people can't turn pages in a book because they might hurt their writing, some might be paralyzed, or their arms might not work. So we invented a device that can help people turn pages in a book. This part turns the pages, and this part makes it flat, and this is how it works. This is our present example. Next step is to learn how long you hurt each page. Next year, we'll learn how to do some simple programming and repeat type ourselves.
Well, this is wonderful. So, how did you guys figure this out?
We had a brainstorming session. Yep.
You had a brainstorming session?
Yes.
Is that right? And then how long did it take you to build
3 months.
3 months?
Oh dear.
That's a big project. But it's working really well, although you got to read kind of fast.
Yeah. I can only read 3 sentences.
Are you-
It's a really
Are you guys able to slow it down and speed it up? No. So that would require sort of a little bit of an adjustment.
Yeah, so we're gonna. It gets kind of. It's a prototype.
It's a prototype.
Yeah.
It's a prototype. It will get refined later. That's my point.
Reset it, guys. Reset it. Bring it to the middle, dear.
Okay.
Oh, stop it. There we go.
So do you guys like inventing things and building things like this? Huh? You guys are very good at this.
Okay.
I'm so impressed. Are you resetting it?
Yeah.
Okay.
Reset. That's our
All right.
special page.
That's the page.
The magic page.
This is wonderful, guys. Can I take a picture with you?
Sure.
Okay, so
But which camera should we look at?
I know it's confusing, isn't it? So here, I'm going to stand. You guys get in front of me, and I'm going to get down on my knee, so we're all kind of even. All right? Okay. So I think where's Pete? Let's look at that camera over there, right over here, and everybody look up and say cheese. Cheese. Well, I'm so proud of you guys. This is outstanding. How did you guys have fun doing this? It was a good project. So you got to keep on learning math and science, and you guys are going to build all kinds of great things when you get older. Huh? You're already a great inventors with your brainstorming sessions and prototypes. Uh-huh. Okay. So what are you guys? What grade are you guys in? First grade?
I'm in first.
You're
and
kindergarten. You're in first and then kindergarten. Excellent. Well, you guys got a good head start. Have you been having fun?
Yes.
Yeah. I know. Well, I'm thrilled to have you guys here.
Have you ever had a brainstorming session yourself?
I have had a couple brainstorming sessions, but I didn't come up with anything this good. Yeah. So you guys are already better brainstormers than I am. You know, I mean, I came up with things like, healthcare. Yeah, it turned out okay, but it started off with some prototypes. We had
Somebody
to.
over there has healthcare for you.
Yeah, well, good. I'm going to go talk to them. So, thank you so much, guys. Good job. Group hug. Group hug.
Good job. Oh, that was a good squeeze.
All right. Thank you, guys.
My head was turned upside down.
No, girls change the world. I like that.
Yeah.
So let's see if you can top this.
It's a hard act to
That's a
follow.
hard act to follow. What's
Hi,
your
Mr.
name?
President. I'm Ruchi. I'm from San Jose, California.
What year are you in school? Ruchi?
I'm a senior.
Fantastic. You know where you're going to go next year?
Not yet.
Not yet? You're
College
still waiting?
decisions are coming out soon.
All right.
So I'm still waiting.
I suspect you'll do okay. So what have you been working on?
I developed a nanotechnology-based biosensor for cardiac health diagnostics. So cardiac arrest is actually the leading cause of death in the world. It causes approximately 1/3 of the deaths.
Right.
And current methods for detecting cardiac arrest are long, they're expensive, they're invasive. So I wanted to develop a device that was very inexpensive, minimally invasive, and very kind of sensitive. So this is actually what it looks like. So it's a silicon wafer-based device. It's based in nanotechnology, so 1 drop of blood would give me an electrochemical readout based on which I can tell you what a certain protein concentration in your bloodstream is. And based on that, I can tell you your risk for cardiac arrest.
So this protein in the bloodstream there's a high correlation?
Yeah, so there's
with-
actually a linear correlation between the change in current that I can detect and the protein concentration in your bloodstream.
So were you already, was the correlation well established, and the question was, how do you detect that protein efficiently? Or
So-
did you also have to try to map that correlation?
So it was to increase the sensitivity of the device. So this device is actually 250 times more sensitive than what's conventionally used.
Right.
So it can detect acute cardiac illness and chronic cardiac illness.
So what was the principle that led you to make it so much more efficient?
It's based in nanotechnology, so I can actually maximize and manipulate the large surface area of the carbon nanofibers. They actually look like this, vertically aligned carbon nanofibers, based on which I can actually just latch on linkers and antibodies and antigens to actually detect certain proteins. So the beauty in this device is that it can be used not only for health diagnostics, but also for biowarfare agent detection or food safety monitoring or environmental monitoring.
So just the concept generally, where you've got a correlation that you can establish using nanotechnology,
Exactly.
You can get a more sensitive, more acute, and quicker and ultimately cheaper technique.
So even cheaper than this is the paper-based sensor. So you can actually touch it if you want to. It's a paper-based sensor. So the idea is something like this could take the form of an insulin test. So you go to CVS, pick it up, use it, and then throw it away.
Right.
And this would be extremely cheap, very economical, and really revolutionize the in-home patient care market.
So this seems like a pretty big deal. So where are we at now in terms of, have you taken what you learned and started to talk to companies that are already in the diagnostic field on this?
So I'm working at NASA Ames, Moffett Field in California. So we're working on that prototyping stage right now, working on making it into a handheld device so you can actually just test on the go or at home. So we're working on that right now.
Well, obviously you're going to continue with your research and ideas in college.
Yes, definitely.
Do you have an idea of what ultimately you'd like to do?
I hope to major in material science and engineering in college and then work as a technology entrepreneur in the Valley.
In the Valley?
In the Valley.
Come on, let's take a good picture.
Right here.
Really proud of you.
Thank you.
Congratulations.
So nice to meet you.
Really nice to meet you. That's great.
Thank you.
Fantastic. All right. Hey guys. Hello everybody.
Good morning.
What's your name?
My name is Corinne Piper.
Good to see you, Corinne.
My name is Christian Sanz.
Good to see you, Christian. Where are you guys from?
We're from Burleson, Pennsylvania, Holly, Pennsylvania.
Outstanding. So what do we got here?
So, we represent the Wallenpaupack area high school, Lemelson, MIT, and Bend teams.
Okay.
So our high school is located on the shores of Lake Wallenpaupack, which is a hydroelectric lake and is owned by our local power company.
Right.
Our power company doesn't allow AC electricity on the water, so the only lighting of the docks that we have is shoreline, so the farther on the docks you go, the less light there is.
Right.
However, our lake has a lot of recreation and lots of wind, so therefore we thought we could use some of all the wave energy that we have and convert it into electricity. So, if you don't mind,
I don't.
would you mind creating some waves in our wave tank?
Okay. So how do you want
Grab
me?
this,
You want me to just
move up and down.
move it? Get some waves going.
Get some waves going.
All right.
So here you see, this is our representation of our floating dock.
Here it is. It's kind of a quiet day out in the lake, but we're starting to get a little breeze.
Yes, very true. And with the servo motor, it generates electricity.
See the light going on, people?
So
Okay.
taking this
Smart.
concept,
Right.
we developed this device.
All right, so inside the device we have two modified gear motors which will act as generators, and they're both connected to a horizontal metal bracket that will extend out over the surface of the water. And then that is connected down to a vertical bracket which is connected to an anchor that floats stationary under the surface of the water. And from there, when this turns, because the device is mounted to a dock which is floating on the lake, as the lake moves with the waves, as the dock moves with the waves, it'll be turning the, yeah, you can, and that'll be generating the electricity that will go from
So
here.
you're basically just converting this mechanical energy into
Exactly, yes.
Now, is there a minimum amount of wave activity required to make sure that a small bulb like this goes off?
Well, actually, the light only needs 3 volts to light, and we can actually generate up to 9 volts.
Yes, so after the electricity is generated, it's charged throughout the day, and it'll be charging a battery pack, which is housed inside here.
If everything got completely quiet, the battery at least would still function.
Yes, yes. And then on top of the device, there's a light sensor that'll be taking light level readings every 15 minutes or so. Once it reads that the light level is low enough, it'll send a signal to the microprocessor, which will power on the light to illuminate the dock. So, covering that.
Here, I'm gonna let you try. Put your palm right on top, and it should
Give it
light.
a second or so.
Uh-oh.
Uh-oh.
There we go.
I was a little worried that it wasn't going to work. Well, that's outstanding.
Thank you.
So have we tested it in the lake itself?
Yes, we have actually. We've tested at local marinas. We've tested on some quieter days because actually our lake is currently all frozen over.
Right.
So some days in the spring we tested over the weekend. We tested 4th of July weekend.
Right.
We tried it one day after school. There's some boats running across it.
Yep, and it
does well.
Great idea.
Thank you.
Thank you, thank you.
Way to go. What year are you guys in school?
We're both seniors.
Okay. You guys know where you're going to go yet?
No, not quite yet.
I guess this is when you start finding out pretty soon.
Exactly.
You guys will do great.
Thank you so much.
Come on, let's get a good picture.
All right.
Come on, we've got to make sure the invention is...
Oh yeah,
is-
here,
All right.
here. We'll put
Do we have a name for our invention?
compact waves.
Pop
Right
back
here.
waves?
Yes.
All right.
Look right here.
All right over here. That's outstanding.
Perfect.
Thank you.
All right.
Thank you very much.
See, I'll be seeing these in lakes everywhere soon. All right. Who's next? We'll go over here. How are you?
Good.
What's your name?
Kate Reed.
Hey, Kate. And what's your name?
I'm Mohammed Saeed.
Good to see you, Mohammed. Where are you guys from?
Cambridge, Massachusetts.
Cambridge, Massachusetts. It is a fine town and got some pretty good schools there last I checked. So what do we got here?
Wheelchair attachments.
Okay.
So, I always wanted a tray table,
Right.
but I couldn't find one that meets my needs, so I
Right.
invented my own.
So you just made your own tray table.
Yeah, and the cool thing about what I have invented is for people in wheelchair that beats the time. So let's say if you have a tray, and after you're done using it, you quickly take it apart. And there are magnets incorporated, so that puts everything together, and then you fold it, and you put it aside in your backpack, which we were not allowed to bring the backpack here. And
Sorry,
put these-
Secret Service.
Put these here,
Yeah.
and then when you are not using the tray, I'm a filmmaker, so I couldn't find something like this, so I made it in 3D printed. It's also magnetic, it doesn't fall out, and it attaches to any camera.
Oh.
Yeah, and then beside that, I also made a cup holder, which is also magnetic. And the cool thing about a cup holder is that it's not just for these kind, it's for mags that you don't see many in the other parts of the world that a cup holder would do this.
So this is really handy.
So that's why it's called
So that-
universal arm, and my goal is I'm from Afghanistan, and I want to produce this so people who can't afford it can buy it for $1 or $2.
Well, and the nice thing is that the concept it's really efficient, but it's relatively simple, and with 3D printing you can start.
Yeah, and I designed it in Fusion, and then I 3D printed it.
That's outstanding.
Yeah, and also there is a canopy that is still in the process, so we are not. I wasn't able to bring it yet.
To get a little bit of shade?
To shade and rain and snow. It just comes from the back and front and clips. So you
all working off of this.
All working. And the main idea here was the two biggest challenge was it should be foldable and everything have to be controlled from the front because many people
you can't
don't realize, to bend backward and you know. So that idea in mind, anything that we invent, I just include this and they go right in here and locks up.
Outstanding.
Thank you.
Way to go.
And thanks for having us here in the
Oh,
White House.
listen, it's my thrill. So what do we got here?
So this is a hand drive wheelchair attachment, which can attach to any wheelchair, and it allows it to be powered in a rowing motion. So like this instead of like this.
Okay.
And so the good thing about that is it's better for your back, it keeps your hands cleaner, and it's also a much more efficient motion.
So instead of doing this,
Yeah, it's like a rowing, like.
you're basically, it's like a lever that you're essentially
exactly.
pulling back and forth.
And so so basically we didn't invent this concept, but the concept of a kind of rowing powered wheelchair has been around. But they all come kind of with the chair.
Right.
And those cost anywhere from $2,000 to $10,000.
Right.
Because ours is entirely 3D printable and completely open source, ours costs $40 and can snap onto any wheelchair.
That's outstanding. How long did it take you to design?
So me and my partner, who's not here today, have been working on this for about 3 months.
Uh-huh.
And it's entirely 3D printable. There's some of our older versions here.
Right.
And you can see it uses a ratchet mechanism. So what that means is there's a gear and there's like a little pokey thing.
Yeah.
And basically it goes around.
Is that a technical term, the pokey
I
thing?
mean, not exactly. But it goes around and basically it locks on the opposite way. And then we invented kind of the dual ratchet, which basically means we have 2 gears stacked on top of each other and can engage one at a time and then disengage the other. So it can go forward and backwards. You can try it out.
Should I try it out?
Yeah.
You sure?
Mm-hmm.
Okay, all right.
So basically I have to unlock you and
Okay.
that hold onto that.
Okay.
And you can just push forward. This one's off.
Oops. Well, I think it came out.
Oh,
So I think, say, it's too loose. It's not
okay.
engaged.
Well then, you can look at this one, the backup.
The
This
backup?
one isn't on the wheelchair right now, but basically it rolls in one
so-
direction.
So you can hear it there.
Mhm.
Whereas this one wasn't catching.
Yeah, it looks like that one's not plugged in, but we can just put this one on actually.
Yeah, well, we don't need, I get a sense that this will work.
Mhm.
But what's amazing is the fact that you can save so much money compared to what the current costs are.
Mhm. It's basically less than 1% of the current.
How'd you get the idea?
So basically through our school, we were given the challenge to hack a wheelchair and to make attachments that would make it better. And so we were kind of researching. Like at first, me and my team wanted to make like something that would help wheelchairs like get up and down curbs or go on and off stairs. But then we realized that those would require like a completely new wheelchair. And so what we ended up doing was just deciding that we would make attachments for it because that was accessible to everyone. And so then we basically came up with the hand drive attachment to make it extremely cheap.
Excellent. Come on, let's take a picture. What grades you guys in?
Juniors.
You're both juniors? Come on over.
Look this way. Here we go.
You guys, junior year is busy. Melena's really working hard. Oh, you guys got a lot of homework all the time, don't you?
Yeah.
It looks like you're enjoying it. All right, we're proud of you.
Thank you.
Keep it up.
Thank you.
Really proud of you. Congratulations. How are you, sir? What's your name? Good to see you, Nikhil. What do we got here?
Well, the title of my project is Latencies, Haptics, and Passwords, Augmenting Password Security Through Keystroke-Based Verification.
Oh, I was reading about this. So the idea would be that each of us have a unique way of typing.
Correct. So the basis of my project was to improve the strength and security of passwords.
Right.
We use passwords for a lot of things now.
Right.
So the goal of the project wasn't to completely get rid of passwords and implement a new system. The goal was to improve the security of passwords by adding a secondary form of authentication to use with passwords.
Right.
But what I wanted to do was make this secondary form not cumbersome, not hard to use, not hard to implement.
Right.
And so what I decided on was it being keystroke based, which in an example, the server or the program that you're trying to log into would first check your password,
Right.
and then it would check your typing style, and then it would let you into the system.
Now, do people have a different typing style?
Right.
Is it because the whole Q? I don't know if people even learn how to type anymore now.
Yeah.
But right when I learned how to type, there was a certain combination, right?
So
that a lot of people learned how to do.
Mm-hmm.
Is it the rhythm and sort of the
So,
strength by which they tap?
So that's something I actually had to investigate in this project, was to see, do people actually type in different ways that you can use to verify someone.
Right.
So to do this, I used 3 different factors. I used one factor, which was what I called action time, which was how long you press down keys for it.
Right.
The second factor was what I called pause time, which is the pauses that you take in between typing 2 keys.
Mm-hmm.
And then the third one was pressure, which is how hard you hit the keys when you type. So these are the 3 factors that I use to distinguish different people's typing styles. And there's a couple more that I could have chosen to use, but these were the ones that I decided to use for this project.
And your findings were that, in fact, they were sufficiently distinguishable that as a secondary form of authentication
Correct.
would work.
Correct. So it would actually work with passwords. So it's not just this alone. So like I said, the password would be checked first, and then this would be checked, and then you can see a 98.4% classification with just these 3 factors. And my feature goals for this project is to add more factors so I could possibly get that closer to 100%.
That's impressive.
Thank you.
Where are you from?
I'm from Zerkley, Pennsylvania.
Fantastic. What year are you in?
I'm in 9th grade.
9th grade? These guys are doing a lot of stuff in 9th grade. Aren't they? Come on, let's get a good picture.
Yep.
Look right here.
Fantastic. Keep up the great work.
Thank you, Mr. President.
Good presentation. Hi.
Hey there, Mr. President.
How are you?
I'm doing very well. Good morning.
Good morning. What's your name?
My name is Sofia Sanchez-Maes, and I'm a high school senior in Las Cruces, New Mexico.
Beautiful place.
So today I'm going to show you how we're trying to create a sustainable energy infrastructure using algae. So the idea to use algae for fuel is nothing new. You've heard all about it, but there's a reason we don't have it at the pump yet. It's costly in more ways than one. It takes a lot of energy to produce energy, and in using traditional methods, it took more energy to produce the fuel than the fuel would ever contain. Now, my project stopped that. So what I did was I utilized a chemical reaction and sort of created a reaction so as to demonstrate a net energy gain. And I do that by eliminating the most energy expensive step of the process. If you look at that table over there, you'll see that the drying of the algae, taking it out of the water and extracting the lipids, takes the most energy in the entire production process, right there.
Right here,
that's
drying and extraction.
152 millijoules of the entire 174. So that's gone away with my method.
Which is? What was the key insight?
Well, the key insight is what's called hydrothermal liquefaction. Now, the idea behind it isn't new. We're doing what's done in the center of the Earth. High temperatures, high pressures, we get fuel. Now that's great, but that also seems pretty energy expensive, doesn't it? Getting it up to supercritical temperatures.
Unless you can afford to wait a billion years or so, and then
kind
of happens on its own.
Well, my generation is kind of the now one.
You're a little more of a hurry.
Yeah, definitely. We want it and we want it now. And so that's kind of what my process does. Using a couple of catalysts, I was able to bring down the temperature to subcritical levels and actually demonstrate a net energy gain. That's all very well. That's exciting, but it's still not enough to make it compete with oil at the pump yet. So what's unique is I used a very interesting algae. It's called Gulderias sulphuraria, and it's from the hot springs at Yellowstone. Now this is a tough little guy. It's one of those on the specials for the most crazy forms of life on Earth. And basically what it is unlike other algae, it can chemosynthesize. It doesn't need sunlight in order to perpetuate itself. And it's very hardy. It can take tough conditions, like the conditions in our wastewater. So what I'm using this algae to do is purify wastewater and create energy. That minimizes the cost for the entire system and will make a significant energy debt in that budget.
How prevalent is this algae if it's found in hot springs in Yellowstone?
Well, we can.
You can duplicate it.
Yeah, we can duplicate
under
it
certain conditions.
And the conditions in our wastewater are those conditions.
Are sufficient.
Yeah. So
they don't have to be at a certain temperature for the algae to thrive?
No, they're pretty hardy. They can take a lot or take a little. But what's really cool about this is they extract contaminants from our wastewater better than the anaerobic bacteria that we're currently using.
So we could use that and then take the algae.
Exactly.
And then
turn it into
energy.
energy. So in every city in the United
It's a twofer.
States, exactly, about 35% of the energy budget in the cities is to purify wastewater. We can eliminate that and maybe even put back onto the grid with this system. So we're actually implementing it right now at our local wastewater treatment plant.
Oh, is that right? You guys are already testing it out?
That's us. And it's working wonderfully. We're hoping to bring it to the big
Where are you
time.
from?
I'm from Las Cruces, New Mexico.
Well, this is really exciting, and I'm assuming you will want to continue working on this when you.
This is a years-long effort that it's been.
So once you're in college, this is going to be.
And the cool thing is getting this to treat our wastewater here in the U.S. is the stepping stone that we need to getting this at the pump, which is one of our ultimate goals.
You You already know where you're going to go, or are you still waiting?
Well, I have a lot of decisions already, so it's choices time.
Right.
But I think right now
Where are you
I'm
leaning?
deciding between Yale and MIT.
Those are good choices.
Definitely. Good problems to have.
But it's a high-class problem.
Yeah.
Come on, let's take a good picture. There's Pete right there. We're so proud of you.
Thank you,
Congratulations.
and it's so nice to meet you.
You're going to do great things.
Thank
I can
you.
tell. Fantastic. Which way am I going? This way? How smart are those kids?